Hello, so now I will be doing presentation on the physical and data link layer, network layer, and transport layer that is in the OSI model layer. Okay, so first we will do introduction to the OSI model for the lowest layer. First, it's Open System Interconnections, which is OSI. And here it is a layered framework for the design of network systems that allow communication between all types of computer systems. So here we can see it consists of 7 separate layers. The lowest one you got physical layer, data link layer, and then the next network layer, transport layer, session layer, presentation layer, and the highest you get application layer. So for this presentation I will be explaining from the lowest physical layer until the transport layer. Okay, now let's go first to the physical layer, which is the lowest layer of the OSI model. It's here, it's responsible sending bits from one computer to another. Yes, and then here it has responsibility sending bits. So it's like this one. It's here. It deals with the setup of physical connection to the network, which is this one, with transmission and reception of signals. So it consists of various network components such as power plugs, connectors, receivers, cable types, etc. So like here, yeah, you can see Ethernet cables, the repeaters, Ethernet hubs, token ring networks. Okay, then let's move to the physical layers function. So first, cables and connectors. So to send data, we need cables to transport the electric signals. So there's many type of cables like twisted cables, coaxial cables, optical fibers, then copper wires. It has like in copper wire it has certain have data flow in form of electrical signals, and optical fiber have data flow in form of light. So the forms of the signals differs between each type of cable. There are also connectors needed such as UTP, BNC, MTRJ. Yes. So the second one, the second, physical topology or network topology. So it's geographical representation of the linking devices. And there are many types of topologies. Okay, now, and then the third one, hardwares, repeaters or hubs. It includes repeaters, hubs. It's repeaters used when we need to increase the energy of signal that was affected due to attenuation, and then hubs are used for multi-point connection. It is responsible for all the physical connection establishment and processing. Then you get the encoding. There are different type of encoding methods. It's a way to change signal into other form to transmit, such as changing analog signal into digital signal, or either way for the transmission. Then the fifth, you get configuration and transmission. So it is like this. You get point-to-point configuration. There is a single dedicated link between the two devices. You get multi-point configuration, which means there is a link through which multiple devices are connected. There's also transmission modes. The first one, simplex. Sender can send, but receiver cannot send half duplex. Both sender and receiver can transmit signal, but not at the same time. And then there's full duplex. Both sender and receiver can transmit signal at the same time. Then last, we got multiplexing and demultiplexing. So transferring different signals through a single connection via different channels is called multiplexing. Then to avoid collision, we can use time division system. At receiver end, demultiplexing used to convert a single signal into n signals. Okay, so here are the significance of physical layer. Data before physical layer is in the form of bits. It is then converted into signals for transmission and then is again encoded back to bits at receiver end. Second, main function of physical layer is to transmit data physically as well as logically from one device to other on the same network. Third, it maintains how many bits per second are sent. Fourth, it determines the direction of data transfer. Fifth, it provides a very important functionality called modulation, meaning that data is transferred in the form of radio wave, optical nerve signal, or electrical signal. So before that, maybe we can create simple network. Here I will be using switch, and for PC, and we will try to connect this with server. Just this. And I will do the IP configuration, and then we will see the layers that 1 and 2, 168, 1, 1, go to 192, 168, 1, 254. Here I will do 192, 168, 1, 2. Here 192, 168, 168, 254. Here, assigning different 30, then 68, 1, 1, 6, 4. Here 192, 168, 1, 4. Did I get? And last PC 192, 168, 1, 1, 2, 168, 1, 254, 192, 168, 5. Okay, just put this one, spread it out. Okay, let's set the server 192, 68, 1, 1. Was here 68, 1, 254. Then on DNS on. We'll create server testing.com. It's 192, 168, 1, 254. Maybe HTTP. Okay, so it worked. Now we will see the processes that created, but first let's set HTTP the protocols, and then TCP. So first I will request to go to www.testing.com. So here the requests are in brown envelope. We'll do the simulation. So here you can see the layer 1. This one, fast Ethernet receive the frame. Then fast Ethernet send out the frame. Now let's see what happens on the server. See? Okay. So the fast, so we can see between each process which layer get active and what is the layer doing. So from here, like this one for example, maybe I will pause it, or maybe I'll finish it first. So like this, it's inbound, and then it get the in layer, which is the fast Ethernet cable. Okay, then second layer, third layer, fourth layer, which I will go into after this. Okay, so that is the physical layer, which is the port fast Ethernet 0. So receive the frame. Then for out layer, it's send out the frame. So it's established. Okay, now let's continue to the data link layer. Data link layer, it is the second layer from the bottom, which is the second lowest, and then it's responsible for the node-to-node delivery of data. Its major role is to ensure error-free transmission of information. Data link layer also responsible to encode, decode, and organize the outgoing incoming data. So here you got the sub-layer of data link layer. You got the logical link control, and then it got media access control. So it's divided into two parts. It got two sub-layers. Logical link control here. This sub-layer of data link layer deals with multiplexing, the flow of data among application and other service, and responsible for providing error message. So it will use protocols such as IP, IPX, ARP, etc. So it will fill in the header portion of the frame, which is multiplexing. Then it will pass that to the MAC layer, which is media access control. Then when on the receiving end, because there is in layers and out layers, so when on the receiving end, which is the in layers, it will the logical link control will be responsible to take the frame from the physical layer, identify the network protocol, and pass on the datagram to the right network layer protocol and the network layer above, which is the multiplexing. Then we got the media access control. I'm sorry, I keep on clicking it. Media access control, it manages the device's interaction, responsible for addressing frames, and also controls physical media access. So it interacts with the physical layer, and it defines here who will have access controls to the media access, that were performed over hardware. And then it also provides the framing of data and into the frames, which is transmitted over the physical layer. These frames contain information about the physical signaling requirements of the medium and also the type of the data link layer protocol in use for the transmission. So here you get the drawings. So net layer, it will use packeting, and it will go to data link layer, and then framing, and then physical layer. So here's are the function of the data link layer. So first you got the framing. So the packet received from the network layer is now it will be known as a frame in the data link layer. And then at the sender side, the DLL data link layer receives packet from network layer and divides them into small frames, and then sends each frame bit by bit to the physical layer. It also attaches some special bits for error control and addressing at the header and at the end of the frame. At the receiving ends, the DLL data link layer takes bits from the physical layer and then organize them into frame and then sends them in the network layer. Second one, we get addressing. So the data link layer, it encapsulates the source and destination's MAC address or physical address in the header of each frame to ensure node-to-node delivery. MAC address is the unique hardware address that is assigned to the device while manufacturing. So you get a different MAC address, like in network, in EC and EC. And third, you get error control because data can get corrupted due to various reasons like noise, attenuation, etc. So it is the responsibility of data link layer to detect the error in the transmitted data and correct it using error detection and correction techniques respectively. And then it adds error detection bits into the frame header so that the receiver can check received data is correct or not. Then fourth, you get flow control. If the receiving speed is lower than the sender's sending speed, then this can lead to an overflow in the receiver's buffer and some frames may get lost. So it's the responsibility of data link layer to synchronize the sender's and receiver speed and establish flow control. So for example, maybe the server can send up 100 Mbps, but your PC maybe only 10 Mbps. So the data link layer, it will configure to send a signal, so the server only it will lower the sending speed, transfer speed to 10 Mbps to match the PC. It can also goes either way. When the server, for example, sending in 5 Mbps, which is lower than the capability of the PC, so it will send the signal. So the data link layer, it will establish flow control so that the server will increase the transfer speed into 10 Mbps, so it can maximize the system. Yes. Then you get access control as when multiple devices share the same communication channel, there is a high probability of collision. So it's the responsibility of data link layer to check which device has control over the channel, and it can be used to avoid collision and loss of RAM in the channel. So here are the four methods of frame synchronization. There is time-based, character counting, byte stuffing, and bit stuffing. And then there are also various protocols in the data link layer, which are as follows: SDLC, the HDLC, the SLIP, and then point-to-point protocol, PTP, link access procedure, link control protocol, and network control protocol. Okay, so maybe we can see the event list. Maybe for example at this one, this information at device PC0. So if you can see the layer 2, it is the inbound layers. So the frame's destination MAC address here we can see matches the receiving port's MAC address, and then the MAC, the physical address, and then the broadcast address or a multicast address, and then the device decapsulates the PDU from the Ethernet frame. So this decapsulates. Then let's see on the outbound here. So the next hop IP address is unicast. So the ARP process looks it up in the ARP table, which is one of the procedure protocol. And then the next hop IP address is the ARP table. The ARP process sets the frame's destination MAC address to the one found in the table. So the server, and then the device encapsulates the PDU into an Ethernet frame. So maybe we can skip a little. So maybe we can see like here. Yes. So here, like the data link layer. So you get the framing, and then it will do the multiplex or demultiplexing. That this will come later. Then let's move on to the network layer. So it is the addressing and routing layer of the packets. It decides the path of the packets through the network. This is done via IP addressing. Source and destination logical addresses are given in this layer. Okay, for IP, this is IP addresses. So it's from here you can see in the drawing, it is very helpful. It's like adds the concept of routing above the data link layer. So when data arrive at the network layer, the source and the destination addresses contained inside each frame are examined to determine if data has reached its final destination. If the data has reached the final destination, layer 3 formats the data into packets delivered to the transport layer. And then otherwise, the network layer updates the destination address and push the frame down here. Push the frame down to the lower layers. Here it updates the destination address and push the frame back down to the lower layers. Okay, so to support the routing, the network layer, it maintains logical addresses such as IP addresses, and then it also manages the mapping between these logical addresses and physical addresses. So network layer function. So here you got the path determination, route taken by packets from source to des, routing algorithm, and then there's also switching, move packets from router's input to appropriate outer's input. And then there's also call setup. For example, some network architectures, telephone, ATM, require router call setup long path before data flow. Here you got the network layer here. This illustration Layer 3 network layer transmits packets between networks and determines the best paths. Then there's also protocols, network layer protocols. Here, the IRP mentioned before. The network layers protocol are as follows. There is IP, primary protocol, in charge of best effort host-to-host transmission. And then ARP maps the next hop's IP address to its MAC or physical address, is for sending packets to the data link layer. There's also ICMP. Hosts and routers use this protocol to handle uncommon circumstances, such as IP packet header problems, inaccessible hosts and networks, and so on. IGMP. Hosts and routers employed to perform efficient network layer multicasting. There's also routing protocols. It's charge of routing table maintenance. So routing here, it is the most fundamental aspect of networking, and then it is the routing protocols. It govern how your data is routed and assist to make that process as seamless as possible. So it is very necessary. Routing protocols, it's necessary because it provides the optimal path selection. It enables loop-free routing, scales up to a very huge size, and then its compatibility with current hosts and routers, variable length support, rapid convergence, reduce update traffic, and is simple to set up. And then it adapts to new situation, the routing protocols. And then it also classified into two categories. It has static routing protocols. So it's when an admin manually allocates the path from the source network to the destination network, and then it's also has the dynamic routing protocols, which enable the routers to automatically append information to their routing table from link routers. So yeah, it has different upside, up and down, between static and dynamic. Then we also get the type of router. Here we get home and small office routers. It just simply pass IP packets between the home computers and the internet. For example, owner's cable or DSL router. And then there's also enterprises routers. It's a more sophisticated routers which connect large business or ISP networks up to the powerful core routers that forward data at high speed down the optical fiber lines of the internet backbone. Then there's also routing, and there's also packet forwarding. So it is a transit of logically addressed network packets from one network interface to another. So it's generally, it has the intermediate nodes, routers, bridges, gateways, firewalls, or switches. So the general purpose computers forward packets and perform routing, although they have no specially optimized hardware for the task. The routing process usually directs forwarding on the basis of routing tables, which maintains a record of routes to various network destinations. So next we get the packet switching, because the network layer is designed to move data from one local network to another local network within an internetwork. So at a boundary of each LAN, a router, it encapsulates frame to read the destination host address contained in the header of the packet. Here we can see here. Yeah, so it has the packet here, which is the source IP, destination IP, So it decapsulates the frame to read the destination host, and then routers use the destination address, and then it will determine which path to use. And then when it's already determined, the router encapsulates the packet in a new frame and sends its way towards the destination end devices, like here. Maybe we can see in here, for example, from this, when we get to this server, or maybe just PC. So for here, packets destination. So here, we got the inbound layers. The packet's destination IP address matches the device IP address or the broadcast address. So it's correct. It doesn't need to readjust, and then the device encapsulates the packet, and it will be layers. Destination IP address in the same subnet. The device sets the next hop to destination. Okay. So for example, like this one. So when the packet already reach its final destination, the frame and packet headers are removed. So the data move up to another layer. Then let's go back to this one, packet switching. It features a destination. It features delivery of variable bitrate data streams realized as sequence of packets over a computer network, which allocates transmission resources as needed using statistical multiplexing or dynamic bandwidth allocation techniques. And then you can also because the router is considered layer 3, because its primary forwarding decision is based on information in the layer 3 IP packet, like the destination IP addresses. So it will have the it will connect multiple networks and then forward packets. So, and then last we got circuit switching, which is another principal network paradigm and a method which pre-allocates dedicated network bandwidth specifically for each communication session, each having a constant bit rate and latency between nodes. Okay, so that's about the network layer. Now let's move on to transport layer. So transport layer protocols, they are responsible for providing reliability for the end-to-end error recovery and flow control. The transport layer protocols also provide mechanism for segmenting and sequentially organizing multiple network layer message into a single coherent message. Here it got different protocols. It got error recovery, flow control, and it will be explained later on. So the function, so transport layer function, it provides logical communication between apps processes running on different hosts. The transport protocols run in end systems, and then here you get the difference between transport and network layer services. If it's network layer, and the data transfer is between the end system. If it's transport layer, the data transfer are between processes. Yeah. And then you get the transport layer services, which is a connection-oriented communication. So it's a connection using data streams that serve as a connection device rather than using datagram model, where in datagram it underlies a connectionless model. And you get B, same order delivery. In the OSI layer, packets provided by the network layer are not guaranteed to arrive in the same order that they were sent, but because of segment numbering, the packets were transferred them to application in an orderly manner, and you get the reliability. It because in the flow of the signals of information, data may congest. It can cause a traffic congestion of data streams. Because of the network congestion, packets may lose during transfer. And then a transfer loss may result to error, but in digital world, errors can be detected. And thus the transfer protocol may check the data if it has error or none, and then an automatic repeat request is also done by retransmitting corrupted data until such time that it corrected. Then you get flow control. Nodes are transmitted from one point to another. It should be properly managed because it should be managed to prevent a fast transmission of data from sending it more data than can be supported by the receiving data buffer, causing a buffer overrun. And there's also congestion avoidance. There should be congestion control, which is to control the traffic entry into a telecommunication environment. So it's to avoid data congestion. And last, we got multiplexing. It's combination of different signals for transmission utilizing single medium or transmission path which provide multiple endpoints on a single node. So here, you get segmentation and reassembly, dividing application data into pieces, but ensures that data is transmitted within the limits of the media, and that data from different applications can be multiplexed onto the media. So here you get the segmentation layer, and then you get the network layer here, packeting, source IP, destination, segment, data link layer. Then it's converted into bits, and then from bit it converted into different signals according to different types of cable. Then it goes to media, signals, bits, application layer, and it will pop that the application layer, etc. Won't be explained in this presentation. So there's also different types of protocols here, but before that, maybe we can show the here, for example, here. So here let's see on the switch, for example, this one. Yes, you get see at the layer, the fourth layer. It got the procedures here. First one, the device receive a TCP push plus ACK segment on the connection to the IP address on port 1026, and it receives segment information, the sequence number, the ACK number, and then the data length. Then it's also the TCP segment has the expected peer sequence number, and it's also process payload data, and then TCP reassembles all data segments and pass it to the upper layer, which is the layer 7. Then on the outbound, it sends segment information, the sequence numbers, the ACK number, and data length. So maybe we can try just from other PC. Testing.com. Oh, buffer fills. Okay, so that's about it. Then last, there's also protocols. There's ATP, Apple Talk Transaction Protocol, CUDP, DCCP, FCP, IL, MPTCP, RDP, RUDP, SCTP, SPX, SST, TCP, UDP, UDP Lite, and Micro Transfer Protocol. So that's all about the data link layer, the physical layer, and then network layer and transport layer. I'm Edric Jansen. Thank you and take care.